Okay, hi everyone. It's good to be back at Devfest. It had been a while. So I am Oscar. I'm an engineer at Google, and I'm here to talk about foundation models and responsible AI. Specifically, I want to cover what are foundation models, what is responsible AI, and what is Google doing toward responsible AI. I was told to make this talk non-technical. I think that was a partial success. So what are foundation models? If you are in part of the developer circles, this is a term that you've probably seen thrown around quite a bit. And I think we have at least one or two more talks that are going to be talking about how to use foundation models. And I can't wait to hear what this group is doing and how they are using foundation models. But for the rest of us, let's try to take a step back here and from the ground up, try to discover what foundation models are all about. So I like to describe foundation models in terms of duck typing. So in duck typing, you look at the attributes first. Foundation models are known for two main things. First, they are large scale, and also they are general purpose. By large scale, I mean that they use large, and I mean really, really large quantities of data. And they're also trained with minimal supervision. You may have heard some fancy terms like self-supervised or semi-supervised. In a more general standpoint, we just say that there's a very minimal version of supervision as part of the training process. For general purpose, models are capable of addressing multiple tasks. By that, I mean that for the most part, prior research were models that were designed for a single task and they did a really good job at it. Now we're trying to step back into more general purpose land, not quite on the general intelligence side of things, but trying to approach that direction. Then they're also used as foundation, as a base for other models that are task specific, and that's the name foundation models. By the way, before I forget, let me start a timer to make sure that we stay on track here. So let's walk through an example. You probably heard about large language models. If you haven't, don't worry, we'll discuss that in a little more detail later. But generally speaking, they are trained using a large corpus of text. I think some of the bigger ones are in the order of billions, if not even over 1 trillion different tokens, or otherwise can be similar to words. The way in which they are trained is to predict what is the next word that is going to come given a previous sentence. They are capable of doing a number of things, including computing embeddings, summarizing, or, and this is very exciting, generating novel text. They are used as a foundation for other purpose-specific models. For example, Google recently released a paper that was talking about a medical knowledge-specific language model. So looping this back to the previous slide, big corpus of text, that's a large quantity of data, check. They predict the next previous words. What that means is that I don't need a whole bunch of experts that are going to be labeling a data set. This is a sort of self-labeled data set. I just have a long enough piece of text, and I have a rolling window where I simply have the previous n words give me the next word. That is a minimal amount of supervision that is required to train this model. Then, as we said, it's able to do multiple things. That's multiple tasks, check. And then lastly, it is being used as a base for other models, check. Therefore, we have ourselves a foundation model. So now, how did we get here? Well, in the world of machine learning, first there are what I describe as the dark ages. Here's where you had your own infrastructure, you had to roll everything out on your own. That means all the way from the training code, you have to write things that were very, very complex, very mathematical, such as loss functions or training procedures, all these things that are typically out of reach for almost everyone except for the very dedicated. So it was just very complex, very costly. Then there was a big leap in technology, and that's the introduction of ML frameworks, for example, TensorFlow. This made machine learning applications a lot more feasible to a much larger group of people. So we saw a big proliferation in the use of machine learning across all kinds of software. But with this came a problem. Once the machine learning models became much more commonplace, we realized that, at least in the machine learning world, bigger is better. So models kept getting bigger and bigger and bigger, and the data requirements kept on growing almost at the same pace. So we had an issue now, and it's almost back to the same as the Dark Ages, is that if you want to have a well-performing model, that was out of reach for most people, except for those that had the amount of resources necessary to train those large models, which was very costly from a computational standpoint. But then we discovered a new trick. That new trick is transfer learning. That meant that you left the hard problem of training a big model to somebody else that had the money and the resources, and then you took that model and then you retrained that model using your own data. What this meant is that you had a much lower requirement in terms of how much data you had to use. And also computationally, it was a lot simpler. So you had a very well-performing model with a fraction of the cost. And this was fine and good, and it worked for a number of years. But now we've entered this new paradigm. And the new paradigm is from the introduction of foundation models. And this is the zero-shot learning and few-shot learning. That is a bit of a technical term, but what it means, in essence, is that we don't even need to retrain models anymore. There's not even a need for fine-tuning. These models are trained to perform in so many different tasks. There's a pretty good chance that whatever you are doing falls under one of those tasks, and you can use the model as is, and you can change the behavior of the model through probing and poking and by providing instructions via prompt in many cases. So that's the evolution of how we got here. Next, I want to cover the different classifications of foundation models. There's many different ways in which we can classify them. This is one way, which is by covering the different types of modality, and that is the type of data that the model deals with. And this is by no means a comprehensive list. This is just a list of different kinds of models that I like to talk about, and I think they're very interesting to share with developers. First, text, and we've already covered a little bit in this area. Those are the language models. But let's discuss in more detail how specifically the PaLM family of models work. This is the Google's version of large language models. I think now we're up to version PaLM 2, but the whole family of models works in a similar way. So with PaLM, you have what is called a sequence of tokens. We can think of tokens as individual words. And the core principle is that you have the model that receives, again, this list of tokens, and the job of the model is to predict what's going to come next. So I have the words once upon a, and I ask PaLM, what is the next word? And PaLM has been reading, again, billions, not over 1 trillion words, and probabilistically says, well, I think that the next word is going to be time. Okay, so far so good. But here's the neat trick. And the problem is predicting the next word is not all that useful on its own. I mean, it's cool and all, but we want to be able to generate an entire sentence or a paragraph, right? So here we apply this trick where now that we've generated the next word, we flip it around, and now we make it part of the input, and we predict the next word. And we can do this so on and so forth until we've reached a point where we are happy with the output and we've computed a full sentence, paragraph, or entire body of text. And that's how the PaLM model works. On the overarching side of things, taking a bit of a step back on PaLM, it goes through several stages. Through the train stage, it does what we just described, but again, reading through billions, if not over 1 trillion words. And its job is to predict the next most likely word. And using the trick we just learned, it's able to compute or to predict, to generate an entire sentence or full text. And that's great, but it's very mechanical. The issue here is that it doesn't respond to the way in which we speak. If I want to learn about what is the capital of France, to be able to have the model respond to that, I will have to say something like, the capital of France is, and then point at the model. That's not how we speak, right? So in the next stage, it goes through a fine-tuning phase, sometimes known as instruction tuning. In this phase, we teach the model to respond to instruction-like text, so that when I say to the model, what is the capital of France? It recognizes that as an instruction, and instead of trying to complete that sentence and continuing that sentence, it responds with a new sentence and says, the capital of France is blah. Next, once the model has been trained and fine-tuned, we go into the inference phase. At this phase, we are no longer training the model. The model is no longer learning. Instead, it goes through this stage where we just provide a prompt to the model, and those are the instructions we give to the model. And then the final stage, the model is going to generate some kind of output. So that's for text models. The other one I want to discuss is image models. There's a number of different image models, and some of them work in different ways. The one I want to discuss here is Imagen, which is also a Google Foundation model. I think this works very similarly to the open source Stable Diffusion, but I'm less familiar with that one, so I don't want to overstate here. For this family of image models, we start with two things. We have an input image, and we have a piece of text. This is called a conditioning text that essentially labels that image. Here, I have a picture of a cat and a description. That's a cat portrait. Next, we're going to add some noise to the input image. And then in this next step, we're going to train a model to predict the denoise image. And this is so far nothing particularly novel. We have plenty of denoising algorithms, both on the traditional side as well as on the ML and AI side. But we do this over and over, and what we're hoping here is that we're using the description as a hint for the model to be able to denoise the image in a way that is context aware. So for example, if you have a bunch of pixels, the model is going to say, okay, it's dark over here, but it's very noisy, but I know this is a cat portrait, so this probably is the eye area. And then there's a whole bunch of cluster of pixels in this area. Oh, I think that's probably where the ear is. That's what we're hoping for, to be able to condition the model using that text. And we do this again many, many times with many different kinds of images, as diverse of a data set as possible. Then we do something very interesting, and is that we just give the model noise. There's no image, there's no portrait of anything here. It's just random noise. And then we tell the model, here's a dog portrait. And the model says, I don't know about that, boss. Actually, no, it doesn't. It's just gonna do whatever you tell it, right? So then the model says, those pixels over here, that must be the nose. Oh yeah, I see it. That is the ear. And then it creates a completely novel image. So it's a pretty neat trick. Again, using stuff that was previously not necessarily novel, but because we have such a big, powerful model, now we're able to trick it into generating images out of pure random noise. Here you can see it in action. This is again using the open source version of Stable Diffusion, and this is from the Keras website. The conditioning here is, this is a picture of a flower. And then each one of these squares, the model is going to say, oh yeah, I see it. So this is right over here. That must be the petal, and the green has to be the stem. And then it creates a novel image of a flower. So that's how image foundation models work. Next up, we have audio. And this is the part that's a little more on the technical side, so please bear with me, but this is, I think, very interesting as well. So conceptually, this is built out of relatively simple blocks, again, non-novel stuff, but then it all comes together to create a complex system. It builds upon two already previously known models. That's the W2V BERT and SoundStream. The first one produces what is called semantic tokens, and the second one, acoustic tokens. If that makes no sense to you right now, don't worry, we're gonna cover that in a second. So on the left-hand side, we have a piece of audio, some kind of recording. And then we run that recording separately through the two different models. The first model produces what they're called semantic tokens. And this is high-level features of that piece of audio. Things like, what are people talking about? And what is the intonation of the speaker? Is the speaker angry? Is the speaker speaking calmly? Then on the other one, we have what is called acoustic tokens. And it helps to understand that this model, named SoundStream, was originally designed to be an audio codec. So the original intent is so that we can convert those tokens right back to audio in a way that the loss of the audio is almost imperceptible to the human ear. The closer to the original source, better, but as compressed as possible. So very important to understand that the whole idea here is to have a compressed presentation of the audio that we can decompress later. Next up, this is where the novel stuff starts, is that we have a whole bunch of past tokens. These are the semantic ones, and we try to predict the future ones. How do we do this? Well, exactly in the same way that we do with the large language models. We have a whole bunch of previous words, and we try to predict the next word, except in this case, instead of words, we have this high-level representation of audio. So maybe the speaker is now speaking very aggressively, but then it's going to calm down, and then it's going to get aggressive again, for example. Once we generated that, we go back to a different model now, and we concatenate the previous semantic tokens, the generated tokens, and we concatenate that with the past acoustic tokens. We run that through a new model, and now we predict future acoustic tokens. Now, keep in mind, these acoustic tokens are supposed to be able to be converted back into raw audio, but it doesn't quite work that way yet. The reason being is that these are very coarse tokens. So even though you can generate audio, it's not going to be very high quality. So we go through one last stage, and you can think of this as a fancy machine learning power interpolation, where you go from a whole bunch of coarse tokens into fine tokens that now are going to generate much higher fidelity audio. Then once you have these tokens, all you have to do is to do what the codec was supposed to do, convert those tokens back into actual audio. I want to show you how this works. Actually, let's see how it works. No audio.
Did you check the box for the audio here? Nope. Stop sharing it.
Again, thank you, Katie, for saving the day. Yeah, it worked before. Let me try one more time, otherwise we'll call it. Check this out.
Forwarding, answered Wolf.
Okay, so you're gonna see a video here. There's a vertical line. Left of the line is the prompt, the audio that is being fed into the model. Anything that comes right to the line, the model is literally generating out of thin air. Not out of thin air, but it's trying to predict what the next sound is going to be. We're going to see that the audio is able to predict not just similarly sounding voices and sounds, but actual coherent speech or even melodies.
Nay, nay, lording, answered Wolf. We know not how to call you lord or lady. We have lived too long in the forest, and are now...
Our first impressions of people are, in 9 cases out of 10, mere spectacle reflections of the actuality of things. But they are impressions of something different and more...
That's probably good enough. I don't know about you, but I find that absolutely remarkable. Again, just completely generated novel audio, given a very small portion of it.
Nay, nay.
So next up we have, do we have it? Next up we have the multi-model family of models. This is a bit of a catch-all and still an active area of research. The whole concept is that it combines not just one type of modality, so not just text or images or audio, but rather a whole bunch of different types. It normally uses the transformer architecture, but again, this is still an active area of research. Different people are going to be doing different things. The one I'm talking about here is DeepMind's Gato model. And they use text, images, and what can be best described as other. In other here is a whole bunch of different things from video game data to robotics to system controls, but of course also includes the language models as well as labeled images. And what they do is that they convert all these different types of modalities into this concept of tokens. And then these tokens are, once again, going from past tokens to generated predicted future tokens. And by doing that in a whole bunch of different modalities, we're hoping that the model is able to generalize this concept of I can predict what's going to happen in the future. This is how we humans kind of behave, right? We see a sequence of images, a video, we kind of see in our minds, oh, I see this is where the video is probably going. And we hear audio, oh, this is where the audio is probably going. And those are not different parts of your brain that are probably all interconnected. So that's the hope here to mimic that kind of thinking. So now let's take a bit of a step back and let's think about what is responsible AI. So we've learned about foundation models and we discovered how powerful they are. But as they say, with great power comes great responsibility. So how do we make sure that we're using this technology in a way that is responsible, in a way that should be deployed? So what does responsible AI mean for developers? I like to describe this in a series of different sections. First, we'll talk about the AI ecosystem. These are different people involved in the AI systems. Then I want to talk about risk and safety. Then about the trustworthiness of AI systems. And then lastly, there's a bit of a catch-all, and I call it the implementation details. As a background, surprisingly to some, at least it was to me, responsible AI is not something new, something that has been studied for quite some time now. And there's some pretty large organizations that have put forth a number of publications that are very much worth a read in their own right. The ones I want to call out here are the OECD. They have their framework for classification of AI systems. The NIST has the AI risk management framework, the AI RMF. The European Commission has the EU assessment list for trustworthy artificial intelligence, which is a mouthful. Fortunately, they shortened it to ALTAI. And then CSIRO has the responsible AI pattern catalog. Worth calling out here that CSIRO is once again at the forefront of cutting-edge research among much, much bigger organizations. So that's very, very good to see. On the AI ecosystem, we have a number of different groups. First, we have the AI actors. These are all the people that influence the AI system all the way from the conceptual stage to the actual deployment and then maintenance of that system. Examples of that could be researchers, the ML developers, DevOps teams, but even bigger groups like policymakers. The reason being is that policymakers are able to enact policy that affect all AI systems, and therefore they're part of the AI actors group. Then we have the end users. These are those that interact with the AI system, maybe directly or indirectly through some kind of layer or application. And they do that to perform some kind of task for a specific purpose. Examples could be external customers, but in some cases, for example, imagine that you have some kind of fraud detection system that's going to go to some internal team of potentially data scientists, right? So it's not necessarily about these are people from my company and then it goes to other company or other end users, but rather in some cases, AI systems are purely internal. Then lastly, we have stakeholders. These are all of those affected by the outcomes directly or indirectly. And this can be an extremely broad group. It can be individual persons, but it can also be animals or living beings, or even entire organizations. Next, I want to talk about risk and safety. To make things simpler, safety is the absence of risk. Okay, so now I only have to define one variable. What is risk? So risk is a function of three different things: the risk sources, the potential events, and the consequences of those events. And I like to think of risk as this machinery that you can tune. There's some knobs and switches. You cannot affect risk directly. You can just say, lower the risk, easy, done. No, you can affect the different components that then affect risk in their own way. And to give you an example, imagine that I have an AI-powered autocomplete. By that I mean you're typing the beginning of a word in your device, and it's trying to predict what is the word that you're trying to type as you're typing it. The source of risk will be my AI model. I can swap my AI model, and that's going to change the risk, but it's not going to eliminate the source of risk. Then we have the potential events. It could be something like an inappropriate suggestion, for example, some kind of offensive word. And the potential consequences of those events are harm users. Maybe I offend my user, or maybe I even affect their mental health in some way. So that's an example of how to evaluate risk and how we can define risk in a more precise way. Then we have trustworthiness, and I want to call out that this is directly from the AI RMF, which, as I said, is worth a read on their own right. Trustworthiness is a collection of things, and the thing about trust, and this is more about human psychology, it is very easy to lose somebody's trust. It is very hard to gain it back. One way to maintain that trust, you have to maintain each one of the components of the trust system. And if you fail in one badly enough, it doesn't matter how good you do in all the others, you are not going to have the user's trust. On the bottom, we have valid and reliable. From a technical definition, valid means that it fulfills the requirements for a specific intended user application. Reliable is very similar to the software side of things. It performs as required without failure. Valid and reliability are put here on the bottom because they underpin the trustworthiness of the entire AI system. I don't care how great and cool and safe and private your app is. If I go to your service and I get a server error, none of that matters. Next, we have safe. We already defined risk and safety, but in this context, safe can be more simply defined as do not endanger human life, health, property, or the environment. Now, this is, of course, very domain dependent. Your definition and your different risks associated with your app or service are going to be very different if you're building an autocomplete app or a complete service, as opposed to something like a medical device, right? So there's going to be a lot of domain-dependent knowledge, and you should absolutely lean into whatever your specific domain is. Secure and resilient. This is very similar to the traditional engineering world, where we need to be protected from attacks and ensure user confidentiality. Resilient, we need to withstand unexpected changes or adverse events. Now, this is more unique to AI, and that is explainable and interpretable. One of the bigger complaints of AI is that it acts as a black box in many ways. Explainable means that the mechanisms of the AI system are understood. In other words, how are those outputs generated? Do we not just feed something in and out we get the output, but we understand how those outputs are generated, and we are able to better understand what the possible failure modes are. Interpretable focuses exclusively on the outputs. So once we have the outputs of the AI system, can we understand them? Can we interpret them? Is it a number? What does the number mean? What is the number range that it can output, right? These are all things that are important to be able to trust the system. Privacy, I don't want to go into too much detail here. This is pretty self-explanatory, very similar to any other software stack. You need to help safeguard human autonomy, identity, and dignity. And then fairness. There's many ways in which this can be described. In this case, I like to describe fairness as free from harmful bias and discrimination. Bias comes in 3 different flavors. It can be systemic, if it's fully pervasive. It can be statistical, if it's the result of something like a sampling bias. Like maybe I try to do a fair system and I go on interview a whole bunch of people, and I do that in some college campus, some university campus. Well, there's going to be a very small cohort of people, and it's going to be a very specific background, right? So that's not going to be diverse enough, and it's very likely to result in some statistical form of bias. And then lastly, we have human cognitive. These are typically known as stereotyping. They have no basis in reality, and it's just a harmful bias. Then on the last side of things, we have accountability and transparency. This is somewhat applicable to the regular software world as well, but in this case, what we mean is that accountable is to be for stakeholders, for anybody that interacts with the AI system needs to be able to assign responsibility to specific components of the AI system. Transparent means that information about the AI system, for example, how it was trained, what data was used to train the model, and the outputs, how are the outputs generated, how do we interpret them, is available to individuals. Once again, the source of this is the AI RMF. Highly recommend reading that. And then last, we have the catch-all implementation details. This is highly dependent to your organization, your company, your app, whatever you're doing. One thing I want to call out, though, is that we developers are responsible for our own actions. We are a crucial part of the AI system, and we shouldn't be afraid to speak up and do the right thing. I like to think of responsible AI in the same way I think of engineering best practices. If the big boss comes and asks me, hey, why can't we run the whole service out of your laptop? Well, I'm going to tell him why that's a terrible idea, right? In the same way, I want to make sure that we developers are educated on what makes an AI system responsible, so we can push back on bad ideas as well, and we can help continue that education further up and down the chain. Then on the last part of the talk, I want to talk about what Google is doing towards responsible AI. So on one side, we have tools for developers. And a lot of the responsible AI things are happening on the ML frameworks themselves. You can see a lot of responsible AI tools and utilities as part of, for example, TensorFlow. But we're also building tools specifically for the purpose of responsible AI that are standalone. Two that I want to mention here are AI Explorables and the Learning Interpretability tool. AI Explorables are a collection of learning materials that help you understand how AI works at a deeper level, and they go into a lot of technical details, and they have some pretty cool interactive visualizations. Highly recommended. They definitely help you better understand how these models work from the inside out. And sorry, not just models, but also concepts and how these models are trained, and a whole bunch of things in the AI stack. So very good educational resources for developers. Then there's the Learning Interpretability tool, LIT for short. I've been personally involved in this project. They recently released the 1.0 version. What this does is that it helps you understand how your model performs by performing a whole bunch of different tests and showing you visualizations, and it helps you kind of poke and probe the model in many different ways. It helps you assess the different biases and how the model has been trained and how the model performs under very specific conditions. If you are working with a team that is deploying or developing their models, highly recommend the tool. AI is, of course, used across a large number of Google products. I don't have time to explain where AI is used all across Google, but you probably know that AI is very pervasively used across, I would say, probably majority of Google products. And the way in which we deploy AI is in accordance to Google's AI principles. And that is, AI should be socially beneficial. We should avoid creating and reinforcing unfair biases, and recall the different biases that we discussed earlier. It has been built and tested for safety very comprehensively. It needs to be accountable for people, and accountability is what we mentioned earlier. People need to be able to assign responsibility and to have some kind of feedback mechanism to the AI systems. We need to incorporate privacy design principles. This is not strictly about AI, but across all of Google engineering products. And we uphold also high standards of scientific and engineering excellence, and it needs to be made available for users that are in accordance to this principle. In other words, we don't want to be just one step removed from something that does not go according to this framework. Then on the other hand, we made very explicit applications that we will not pursue. These are things that are likely to cause overall harm, weapons or the kind of devices that can cause direct injury, surveillance that violates international accepted norms, or purpose that contravenes international law or human rights. So what are some examples of the things that Google is doing in accordance to these principles? we try to avoid creating or reinforcing unfair bias by avoiding unjust impacts on people. And one of the examples that we like to use here is face recognition systems. The way that your face looks or what glasses you wear or your skin tone should not matter. Face recognition systems should work for you as well. You can see this in a number of different products, from Google Photos to Pixel phones. The products should be built and tested for safety. You should avoid unintended results that create risks of harm. An example that I like to use here is that we did some very extensive adversarial testing of BART, that is Google's front end for the Palm large language models. And a story that I like to tell here is that there was a essentially company-wide call out to test BART before it was released. And I was telling a colleague of mine about it, like, hey, this website or this internal site we can go to, and then there's this chatbot, and you're supposed to say mean things to it, or see if you can get it to say anything mean back. And then my coworker she looked at me very seriously and said, I've been training for this my whole life. AI systems, as I said, need to be accountable to people. We like to provide plenty of opportunities of feedback and be able to explain what is happening as it goes. The example here is again on BART. If you look at the BART's website, you can see that the user interface has a whole bunch of different buttons you can press, thumbs up, thumbs down, but you can also provide direct feedback. You can even rewrite what BART is telling you, saying, I think you should have said this instead. And these are things that are then used to better improve the model in a way that we think is fair to everyone. And then the last example I want to show is that we incorporate privacy and design principles. This is not exclusive to AI, but it's a crucial component to trustworthy AI systems, which is why we discuss it here. We like to provide plenty of opportunity for users to provide consent and to give them notice. And this is just one example of a recent redevelopment of the Google account settings on Android. It helps you see how your information is being used and how we keep it. And that's all from me. We have the Responsible AI blog, which is intended for developers. You can see that the URL there. We also have more information about how Google is using AI and responsible AI at ai.google. And yes, that is a valid URL. You can reach out to me at the platform formerly known as Twitter, or my email address is over there. And again, that's all for me. Thank you very much.
Thanks, Oscar. Now, does anybody have questions, comments, thoughts? I'm back.
Okay. Can you hear? So a lot of thoughts in my mind now, but mostly related to perhaps you should call it labeling the input, either with the language, human language, or attribution of a particular GPL license for source code, Apache, etc., and getting that at the output. So, for example, when you train your data, do you label if that text is English or Spanish or Mandarin, or it's GPL or Apache license? And tailoring that to responsibility and the last part of your talk, because we sort of say that we're in the post-truth world. Can we all, how can we help validate the output? You know, like if we're experts in the field, we're gonna ask the question, we're gonna say, oh, this is kind of off. I know how to check it. But if I'm a newbie, I'm a junior in so many fields, right? How can AI help me verify the output?
Okay, great question. Let me tease out a few of the different concepts you mentioned here. So you mentioned labeling. One of the core concepts of foundation models, like I mentioned earlier, is that they are minimally supervised. There's a minimal amount of labels. So in many cases, for example, in the large language models, we don't tell it this is English, this is French, this is Portuguese. We just feed it the tokens one at a time, and it's going to hopefully sort it out on its own. That's the goal here. On the license side of things, that's a whole different animal. And of course, we don't want to use inputs that have restrictive licenses that should not be used. Then what you're mentioning later is how do we validate the outputs? There's different ways to do that. And this is definitely within the realm of responsible AI. And one of the things that I think is a very active area of research that I think we should definitely do better is what is called source attribution. So when the model is telling you something, how do we verify that that something is technically accurate, technically correct? The good answer, or the positive side of things, is that this is very actively being worked on. We're making some tremendous progress. And if you look at BART, for example, there's now different ways in which it links back to Google. And you can actually go back to Google and validate the information from actual sources on the web. On the other hand, the less positive side of things is that I think we still have a long way to go until we can fully trust these systems, because right now they hallucinate a lot, right? They generate text, and there's no way for us to know if the text just looks coherent or if it actually is grounded in reality. So yes, there's a lot of work in source attribution, but we still have a long way to go until I think we can have a fully trustworthy system.
Any other questions? Oh, yep.
Hi, I was wondering what's the process for countering hallucinations or kind of preventing them? Or is that just something we're going to accept like for forever kind of thing with AI models?
Good question. I don't think it needs to be accepted. I think that we need to continue to research ways to do it. I think that we are taking a sandwich approach. First, on how these models are trained so that they are taught to hallucinate less. And we've discovered things like, for example, if we ask the model to cite their sources, in some cases, they're going to make up the sources. So that's no better, right? Then on the other end of things is that once the model has generated an output, you can have another layer before you just provide that output to the user, in which you are filtering, modifying, editing, so that you know what you're responding to the user is more realistic, or there's less hallucinations. So again, this is a multi-layer approach. Still a very active area of research, but to answer your first question, or your last question, no, I don't think we should accept that as the state of affairs. It's still very, very early on, still very experimental technology. I don't think we should write it off just because it doesn't work quite perfectly yet.
Hey, thank you. Can you hear me? Okay. So, I mean, the obvious thing is there's tons of foundation models that are coming up now. So with the frame of work as developers working on task-specific AI applications with a responsible AI hat in mind, like, how do you imagine like leveraging multiple financial models, and then how would you rank them?
How to work with different foundation models is a matter of testing. I mean, this is you're now in the line of some fundamental engineering principles, right? You don't just try things and test in production, so to speak, right? So you need to have some process by which you can evaluate these models, and that's going to be fully domain dependent. If you're talking about foundation models, then yes, we have a whole bunch of benchmarks, but that's very unlikely to be applicable to your specific task. So one of the recommendations we give developers is that you develop your own set of benchmarks specific to your domain, specific to your task. But that's not enough. You also need tests with real users. And by that, again, please do not test in production, but rather have some form of beta testing, or even some small scale in-person testing, so people can provide you that feedback and give you that accountability for your outputs. And then to answer your other question, how we evaluate all those different models, just keep trying new things. It's both good and bad that the landscape is changing extremely rapidly, and maybe the best performing model today is going to be not even top 5 next week. So this is changing very, very fast. I don't know if we're going to approach a point where things are going to stabilize, but it is very exciting for us developers, but at the same time, as you all know, probably pretty hard to keep up with.
You talked about privacy and also large models of data sets. Do you see both as
mutually exclusive?
I think that privacy means different things in different contexts. In terms of trustworthiness of an AI system, the privacy is of the users that are interacting with that model. So that comes at a whole different stage compared to the training phase. And what you use as training data does not necessarily and probably shouldn't overlap with the way in which people are using those models. So I don't think they're mutually exclusive. I think that you need to discuss privacy in the context of responsible AI is once the AI system has been trained and built. But there's also, as you mentioned, in the question of privacy in the training side of things. And I didn't discuss that at all, but I think it's very important that we respect user privacy on all ends of the spectrum. But those are completely separate questions that need to be treated in very different ways. Does that answer your question? Kind of. What it is?
So do you build upon your models? Do you build upon your models with the data of people using the AI? Like, if I'm using Google Assistant, you've built your model around, you know, existing speech and you train that. Do you further train it on queries that people are asking?
Okay, great. That's a great question. So it entirely depends on your specific use case. And if you do that, you should absolutely provide abundant consent opportunities for the user and a lot of notices to make sure that that's very, very clear. I think that is something that big tech has been seen as failing at doing, and I think that we are trying to hold each other accountable for that. I think there's better ways in which we can do it, and we can simplify even further the way in which this is explained, because in many cases you have this very large, complex terms of service, right, that every company has nowadays. I think we can do better at trying to not use that as a cop-out saying, oh, you agree to this, right? So that's why we had made the changes, for example, in the Google account that I mentioned earlier, the account privacy settings. We're trying to incorporate those principles across as many different products as possible.
What do you think is the best approach to combating the misattribution of intelligence to these models?
Combating the misattribution and intelligence?
The misattribution of intelligence to these models.
I think that this is similar to the previous question for source attribution, and that is the dual-sided approach. On one side, we need to make sure that as we are training, we are conditioning these models to hallucinate less, and that's perfectly doable.
More in a social context, more like how do we make sure that people are not claiming that these models have any kind of intelligence when they are just predicting the next word or predicting the next statement?
So I guess this is more on the side of educating the general population about this is not magic, right? This is just zeros and ones all the way down. This is very difficult when models are becoming more and more capable, and it becomes very easy for us to anthropomorphize. And I fail at this myself. In many cases, I talk about the model as it goes like, a he or she, but we need to understand that these are machines that we have built, these are machines that we can control, and these are machines for which the behavior can be tuned. I think that there's something that is still in the early stages, and it is difficult not to get too excited. So I think that maybe one of the solutions here is to control our own excitement and to be more grounded in, again, these are just pieces of technology that we should be able to keep tabs on.